Okay, so now in 12.2, we're going to go ahead and we're going to look at what happens if our graphs, our scatter plots are not linear. What do we do if it's not linear? Everything we've done so far, everything's been pretty linear. So now what happens if it's not linear? Then what we try to do is we try to do what we call a transformation of our data. We transform the data so it straightens our pattern, our curved pattern, into a straight line. And once it's in a straight line, then we can use our regression line to help make predictions of what's going to happen. So if the conditions for inference are met, we can then estimate or test a claim about the slope of a true population regression line. So the first thing we're going to talk about is how to transform with powers and roots. So usually when you look at something, you're going to kind of want to see, hey, does that look like a cubic curve? Does it look like a parabolic curve? Does it look like a square root? So look at the scatter plot and kind of get an idea of what that looks like, which is why we ask you to make sure you've had Algebra 2 first before you take this class. Because usually in Algebra 1 and Algebra 2, we really look at what type of picture is it? What does it look like? So that way you get an idea. So now when we get into stats, we can transform by using squares, square roots, cubes, cubed roots, power 4, fourth roots, so on and so forth. So what do? Well, if you notice that it looks like a quadratic, then what you're going to want to do is you're going to want to square one of your variables. And then graph that. So if I square the x value, then what I'm going to do is I'm going to want to graph y and x squared and see if it straightens out. And if it doesn't, then I'm going to want to flip it around. So then I'll square my y and I'll graph y squared with x and I'll see if it straightens that out. And then we can look at residual plots also to see, is it linear? And then if that doesn't work, we can always do the roots. And we just go through and we do trial and error. And then once they both look linear, you're going to graph the residual plot to determine which transformation is truly the best. And if you don't know what power to choose, you just keep guessing, you keep trying it out. Now for our purposes, because that can sound really complicated, what we're really going to do is we're going to identify from a scatter plot what transformation was performed. And then from there, we're going to write a prediction equation. We're going to make predictions, and we're going to identify which model or transformation will be best. So a lot of times, I have performed those transformations for you, and I've given you a graph, and I'm wanting you to tell me what works best. Because you could easily spend hours trying a ton of different transformations when really you don't need to. So what we'll do is we'll do the transformations, and then you need to analyze the data and tell me which one's the best one. Okay, so we're going to be looking at power models, which means that usually our x is to a power or our x is to a root, but not always. Where you might see something like this, area. So area of a pizza related to diameter would have an equation like this. Distance that an object is dropped from a given height, that's a quadratic type. The time it takes a pendulum to complete a 1 back and forth swing, again, using powers and intensity of a light bulb. Now we're starting to talk about not just powers, but reciprocals. So now putting x on the bottom of something. So that's something else we're going to look at. Okay, so here's our sample problem. What does a country's under 5 child mortality rate tell us about income per person for the residents of that country? Here are the data and a scatter plot for a random sample of 14 countries in 2009. So what we're seeing is that as I increase my mortality rate, are the dots going up higher or are the dots going lower? And we're starting to see that this value gets lower. See, because the dots here, they're up, and then as I go farther this way, the dots come down lower. So it's almost like it goes down in a negative motion here. And so that means as mortality rate increases, income decreases. Which makes sense. Typically, there's going to be more health issues, more problems for people who have less money. Okay, and then, is it linear? So usually as we evaluate, we see what's happening. Okay, as one increases, the other one decreases, and this is definitely not linear. And so now that we've identified it as not linear, we can work on transforming these variables. So what I did is I applied two different transformations. I took the numbers down here, these, let's change colors. So I took the X values, the mortality rate, and for each mortality rate, I did 1 divided by that number. So if this was a 20, I would change it to 1 over 20. And I do that for each one of those. So now what I have is I have the reciprocal of the mortality rate. So really just 1 over mortality, which I just told you right here. And I kept my Y's the same, the income. And so as we can see, that's no longer curved. Now over here, I left mortality rate the same, but then I did 1 over income. So I did the reciprocal of the income. And you can see both of them have really straightened out. So now the question is, which one looks more appropriate? And my guess would be the second one. Now, why would that look more appropriate? Well, when I look at this, I see this huge bunch right here, and I see these points out here, which we would call influential points, because they are way far off from the main group, and this one's kind of higher up than the others. This one's just really far off, and so they're really going to influence things because they're way far out there. And so it's a little bit harder to tell, would this really be linear? Because if I were to do kind of a line of best fit here, just by looking at this group, it wouldn't really affect this. So these dots would really pull this line up and make a huge difference. So now when I look over here, it's not quite as crowded. These aren't really as crowded. These are still kind of far off, but nowhere near what they were over here. So now when I'm looking at it, it seems like it fits the data better when I kind of estimate that line of best fit. So we have more scatter, less influential points. And not really that the points are not influential anymore. Those points are probably still pretty influential, but they don't have as much of an influence. They're not as extreme as the other ones. Okay, so now that we kind of identified that we thought transformation number 2 was the best, now we're going to go ahead and look at the data. And so here is our residual plot. And what we're going to go ahead and do is for transformation number 1, we're going to go ahead and write our prediction equation. So for transformation number 1, our y-intercept would be 869. So our, let's see, y equals, what was y for this one? Y is income, and I can tell that from up here. So my income is equal to 869 plus our slope, 104,868. Take a better look at that. And then this is 1 over our mortality rate. And so that's our prediction equation using the variables from the problem. So now let's go ahead and do transformation number 2, which would be, let's see, we did y, so 1 over income equals, let's see, and these are really small numbers, negative 0.12345, plus our slope 1, 2, 3, 4, 5, 1, 4, 5, and 829, and times our mortality. And so now this gives us 2 different things that we can do. So now what we can do is we can predict the income for a person from Turkey, which had a child mortality rate of 20.3. So what we can do here is I can predict my income. So my y hat, I'm going to go ahead and put the y's in there, equals 869 plus 104,868 times 20.3. Oops. Times 1 over 20.3. And so now that we've plugged that into that equation, we can figure out what this would be. So we would predict the income to be $6,034.91. Now over here in the green, I would have 1 over my y hat equals, and I'd go ahead and I'd plug in that negative 0.12345 plus 1, 2, 3, 4, 5, 829, and then we're timesing by the 20.3. And so then we get 1 over y hat equals 1.62437 times 10 to the negative 4th. So how do we figure out what y hat is? Well, I put that over 1. I do a little mumbo jumbo cross multiplication. So this, when I multiply, is equal to this. So I get y hat is equal to, let's see, 1.62, so on and so forth, times y hat equals 1, and I divide by the 1.62, and I find that y hat is 6,156.23. Pretty darn close, both around $6,000, but which one is really the best fit? So how do we know? Well, when you look at the scatter plots, this one again has that bunching. We've got some, even more influential points over here. And then here we're still seeing some influential, but way more scattered. Not a lot of trumpeting, but maybe a little bit of trumpeting. But how do you tell the best? The easiest way is start looking at our R-squareds. So 83% of my y value will be attributed to my x value using this equation. 91.4%. Oops, sorry. I'm using the wrong one. I'm using the adjusted version. So we want just r squared. So 84 versus 92. It's still pretty much the same. And so we can use that to help justify which one is a better fit for us. And so we were right. Transformation number 2 was the best fit. And so that's what we're going to be looking at. Writing these equations, solving the answer. So this is transformation number 2.